Hello friends, I'm Kumar going to discuss a topic called refrigeration. And before the refrigeration, I would like to say something about the basic terms which we are going to discuss in this topic. So first we will go to know what is refrigeration, and the second one thing we are going to discuss it how and why the cooling process is different from the refrigeration. Because many of the students they are getting confused that the refrigeration is equal to cooling. Third one thing we are going to discuss is relation with the other processes called as like thermodynamics, heat mass transfer, and IC engine. So in this topic we will cover what is the basic difference between the thermodynamics process, heat transfer process, IC engines, or power plant. And the fourth one we are going to discuss is unit of the refrigerator. And then we are going to discuss the Carnot refrigeration cycle, and at the last we will discuss about the COP. In this topic we will discuss COP of the refrigerator, then COP of heat pump, and then the efficiency of the engine. And finally we will relate them to each other. So come to the first point, refrigeration. What is refrigeration? Refrigeration is just maintaining temperature of the space of a particular space or predefined space lower than the surrounding temperature. Suppose if we call as this is our space where we have to maintain our temperature, and suppose this particular area has a temperature of 80 degrees initially, and outside atmospheric temperature is around 32 degrees. First, as we are seeing that here the temperature is high, and we have to control the refrigeration. We have to do here refrigeration. Sorry. So, if we reduce its temperature up to 28, 30, 31, any temperature that below the atmospheric temperature, it will show the refrigeration is working in the particular space or space. And now coming to the topic number second, that is difference from cooling. Cooling is a process of heat transfer from a high temperature body to the lower temperature. It is not refrigeration completely. So, for the cooling process, we would like to give an example of cup of coffee. Cup of coffee. Suppose a cup of coffee is there, which temperature is 80 degrees centigrade, and the atmospheric temperature is there 32 degrees. 32 degrees centigrade. Initially, when we put this cup of coffee in the atmosphere, this temperature was 80 degrees centigrade. But after some time, this will go to the 32 degrees centigrade. That is equal to the atmospheric temperature. This is where zero law of thermodynamics occurs. That a body at any temperature, if it is put in the atmosphere, it will go to the 32 degrees centigrade, and so as this cooling process occurs. So the cooling process is only the heat transfer of higher temperature body to the cooler temperature body. But in this cup of coffee, if we maintain its temperature to the lower than this atmospheric temperature, that is less than 32 degrees. So here it is refrigeration. Now we can say that we understand actually what is the refrigeration and what is the cooling process. So I am going to revise this, that refrigeration is nothing but just controlling or maintaining the temperature of any space, predefined space, lower than the atmospheric. And cooling is a process of heat transfer from higher body to lower body. Now coming to the third topic, that is our relation with other thermodynamic processes. As we know, energy interaction. First of all, I would like to discuss that energy conservation law. Law of energy conservation says that energy can neither be created or nor be destroyed. Energy can neither be created or nor be destroyed. But it can change from one form of energy to another form. So, as energy conservation says, energy can transform from one form to another form. So there, energy conversion can take place in three forms. First one is mass transfer via mass transfer. Energy can interact or transfer from one form to another form by the transformation of mass. Second one is heat. If we exchange heat from a body to another body, the energy interaction will take place. So via energy interaction, heat interaction. And the last one is work interaction. Work interaction. So these three ways are the most preferable and concluding transfer energy from one form to another form. And here, if heat is there and work is absorbing, if heat is there and work is absorbing by the system, so in energy interaction, if via heat and work, these two methods, if work is absorbing and heat is there, these two methods give us the RAC, that is refrigeration. But if work is produced by the system, work is producing by system and heat is there, it means heat is taken by the system and work is producing by the system, that we can say it as it is IC engines. IC engines. Or we can say it as power plant. plant. And now, if mass transfer takes place as well as heat transfer takes place, then this will give bond to the heat and mass transfer. Heat and mass. Mass transfer. As we all engineers are studying these topics. These all are different subjects, but these all topics, these are 5 topics, are coming from a single origin, that is energy interaction. So first, I am going to revise it as energy interaction takes place by 3 ways. 1 to 3. This is mass transfer, heat transfer, as well as work transfer. If mass is transferring and heat transfer is there, so we study it in heat mass transfer. If heat is there, heat is taken by the system and work is produced by the system, then this is give a bond to the IC engine or power plant engine. And now heat is there, taken by the system, and work is absorbing by the system, then it gives the bond to the refrigeration system. Where we are studying now and what we are discussing now. In IC engine, there is also difference. If combustion takes place inside the cylinder, that is called IC engine. And if the combustion takes place outside of the cylinder, that is called power plant. So forget about all these things, heat mass transfer, IC engine and power plant. We are just concentrating on this refrigeration. Now we all know what is refrigeration, what is cooling, and from where it is originated, the refrigeration topic, and how it works. That is what are the resources used by the refrigeration system, that are, as I showed you, heat and work. Now coming to the third topic, that is unit of refrigeration. Unit of refrigeration. There are 3 units which gives us the unit of refrigeration. First, that is called 1 ton of refrigeration. 1 ton of refrigeration. That is mean 1 ton of refrigeration is just equals to the 3.5 kilowatt or kilojoule. Or kilojoules per second, or 210 kilocalorie per minute. So these are the unit of refrigeration. 1 ton of refrigeration is just equal to 3.5 kilowatt or kilojoule per second, and 210 kilocalorie per minute or 50 joules per second. So, what is 1 ton of refrigeration? Now, in the physical meaning of 1 ton of refrigeration, it means that 1 ton of water going to change its phase at 32 degree Fahrenheit to the 32 degree Fahrenheit ice. 32 degree Fahrenheit ice. cooling for an ice in 24 hours. Means this is the physical meaning of refrigeration. Now coming to the topic, next is our Carnot refrigeration cycle. Carnot refrigeration cycle is the basic ideal cycle. It is also called as an imaginary cycle because any refrigeration cycle which produces 100% efficiency, it is not possible. So, as a Carnot cycle, if we draw the PV diagram, the first one is the compression of fluid or refrigerant. In the Carnot cycle, the first one process is reversible, adiabatic compression, that is P to the power gamma is constant. So, in this, we are going to increase the pressure of the refrigerant. We are going to increase the pressure of the refrigerant as well as the temperature of the refrigerant. Now, from 2 to 3, isothermal. From 1 to 2, it is reversible adiabatic compression. From 2 to 3, it is isothermal heat addition. So as we know, in the PV diagram, reversible adiabatic process and isothermal process both are curved, not a straight line. And after that, it again reversible adiabatic expansion 3 to 4, and then from 4 to 1 it goes to isothermal. From 3 to 4 it's reversible adiabatic expansion. And from 4 to 1 it is isothermal heat rejection. So, as we said, in the refrigeration process, we have to maintain our temperature lower to the atmosphere. So, if we draw this diagram in the PS diagram, temperature versus entropy, then this diagram will look like this. The first one process called reversible adiabatic process, that is reversible adiabatic compression, will look like this. 1, 2, straight. It is a straight line on S entropy, where S1 is equals to S4. And now the process from 2 to 3, the isothermal 3, it will stop. It is also a straight line because isothermal processes are straight lines in the TS diagram. And then from 3 to 4 again, it goes down like this, and then 4 to 1. Since in refrigeration or in thermodynamics, if a process is anti-clockwise, in anti-clockwise direction, it shows that it absorbs the work, and if it is clockwise, then it gives the work out. Students are making so much mistake in this particular indications. They take it as like this. This is what they are going to do. 1, 2, 3, and 4. Remember, this is not a refrigeration cycle. It is a cycle of Carnot engine, but it is a cycle of Carnot engine, not a Carnot refrigeration cycle. So, come to here. Here, water temperature TH, and here it is TA, where this is Q heat supplied and Q heat presented. Now, coming to the next, that is COP. For the COP, we will go with this diagram, which is called temperature entropy diagram. For the COP is also called as EPR. COP is coefficient of performance or energy performance ratio. For any engine or any system, we have to know, or we have to understand that what is its efficiency, so that we can easily understand that in how much input it will give how much output. So to know the input output ratio, we have to calculate the COP or EPR. For this COP, we will go to this. If we look here our system is there. This 4 to 1 process, this gives us refrigeration effect. Refrigeration effect. And process 1 to 2, it is working because here compressor is working and temperature is not recovering device. For this, refrigeration is QL, which is here, and as we know from the law of thermodynamics that W in a cycle, summation of work is equal to summation of heat. So that if we can calculate this Q net, we can show that what is W input, that is equals to QH minus QL. So refrigeration effect is the effect that comes from refrigeration effect is the amount of heat which we have to extract from the space. So that since COP is equals to RE upon work input, so for this, if we go to here, the temperature is PL, the dq. From this diagram, TS diagram, from TS diagram, dq at 4 to 1 is equals to TL s 4 minus s1, and dq 1 to 2 is equals to for this W input TH minus TL S3 minus S2. So this is our RE. On putting these values from equation 2 and from equation 1 into the equation number 8, we can get the COP. That COP is equal to TL divided by TH minus TL S4 minus S1 as S3 minus S2. Since S3 minus S2 is equals to S4 minus S1, so this S4 minus S1, S3 minus S2 cuts, and here it comes TL upon TH minus TL. So this is the COP of refrigerator. One more important thing we have to say that Carnot engine COP does not depend upon the refrigerant that which refrigerant they are using. COP is only a function of COP of refrigeration cycle is only a function of temperature limits which are there, this one and this one. So coming on to the next, we get COP of R is TL upon TH minus TL. As here our refrigeration effect is, to maintain the temperature lower than the atmosphere. Now if we talk about the heat pump, there are two pumps. First we have to understand that there are two pumps. First one is water pump and second one is heat pump. Heat pump is used for pumping the heat from lower temperature to the upper temperature. So that in case of heat pump, RE case maintaining the temperature higher than the outside or atmosphere. So here the COP comes, COP of heat pump is equals to T of higher upon T of higher minus low. So if we relate the COP of heat pump and COP of, so this is TH upon TH minus TL. If we subtract 1 from both sides, then COP of heat pump is minus 1. COP of heat pump minus 1 is equals to TH minus TH plus TL divided by TH minus TL, which comes TL upon TH minus TL. of heat pump is equal to 1 plus COP of refrigerator. COP of refrigerator. And as we all know that efficiency of engine is 1 upon COP of heat pump. So from here we related the COP of heat pump is equals to 1 plus COP of refrigeration, and the efficiency of engine is equals to 1 by COP of heat pump. So with these topics I am going to finish my presentation. As I says that I will relate at the end of all things, I will relate the COP of refrigerator as well as heat pump and engine. Here it comes, and hope it will help you. Thank you.